Landing a human on Mars and bringing them back is the ultimate engineering final boss, a mission so complex that it makes the Apollo moon landings look like a weekend camping trip. To understand the scale of this nightmare, you first have to look at the orbital mechanics. We can only launch to Mars every 26 months when the planets align, meaning if you miss your window, you're stuck on Earth for 2 more years. Once you do launch, you face a grueling 7-month transit across 140 million miles of void, where the crew is bombarded by galactic cosmic rays, GCRs, and solar particle events that act like microscopic bullets, shredding DNA. By the time the astronauts arrive, they will have already absorbed 60% of their career radiation limit, and their bones will have significantly thinned due to 210 days in 0G, even with intense daily exercise. The 20-ton landing nightmare. The real terror begins at the Martian atmosphere. Mars has a Goldilocks atmosphere in the worst way possible. It's just thick enough to create 5,000 degrees Fahrenheit friction heat during re-entry, but too thin to provide enough drag to slow down a heavy spacecraft with parachutes. When we landed the Perseverance rover, it weighed about 1 metric ton, and we barely squeezed it onto the surface using a sky crane. A human mission, however, requires a lander weighing at least 20 to 40 metric tons to carry life support, habitats, and a return rocket. Parachutes physically cannot handle this weight in Mars' 1% air. To solve this, engineers are betting on supersonic retropropulsion, a mind-blowing technique where the lander fires its massive engines directly into the supersonic wind as it screams toward the ground. This creates a propulsive shield of plasma that slows the 40-ton beast from orbital speeds to a soft hover in just minutes, turning Mars into a gas station. But getting there is only half the battle. The rocket equation states that if you try to bring all the fuel needed to return home from Earth, your rocket becomes so heavy it won't even leave the launch pad. This is where In-Situ Resource Utilization, ISRU, comes in. To get back, we have to turn Mars into a chemical factory. Years before the humans arrive, an automated Sabatier reactor must land and begin sucking in the Martian atmosphere, which is 95% CO2. By mixing this with a small supply of hydrogen brought from Earth, the reactor triggers a chemical reaction. CO2 plus 4H2 yields CH4 plus 2H2O. This produces methane, rocket fuel, and water, which can be split into oxygen. We are literally manufacturing our ticket home out of thin air. If that machine fails to produce enough fuel while the astronauts are in transit, the mission becomes a one-way trip, the 18-month survival marathon. Once on the surface, the crew doesn't just plant a flag and leave. Because of orbital alignment, they must stay for roughly 500 days, 1.5 years, until Earth and Mars get close enough again. They will be living in 38% gravity, which we still don't fully understand the long-term biological effects of. Their habitat will likely be covered in several feet of Martian soil, or regolith, to act as a radiation shield against solar flares. They will have to survive global dust storms that can last for months, blotting out the sun and rendering solar panels useless. This is why nuclear power, specifically small-scale fission reactors like NASA's kilopower, is essential for a Mars base. Solar power is simply too unreliable for a life-critical mission in the Martian winter. The first ever launch from another planet. The most high-stakes moment of the entire mission is the launch of the Mars Ascent Vehicle, MAV. This is a rocket that has been sitting in the freezing, dusty Martian environment for 2 years, and it must fire perfectly on the first try. It has to carry the crew from the surface back into orbit to rendezvous with the Earth Return Vehicle, ERV, waiting above. There is no mission control on Mars to help. The launch is entirely autonomous. Once they dock with the ERV, the crew begins another 7-month trek back home, the final 27,000 miles per hour slam. The mission ends with a violent re-entry into Earth's atmosphere. Because they are coming back from deep space, they hit our air at 27,000 miles per hour, much faster than a return from the International Space Station. The heat shield will have to endure temperatures that would melt almost any known metal. As of 2026, NASA and SpaceX are using the moon as a proving ground via the Artemis missions to test these exact heat shields and life support units. We are currently in the phase of perfecting conducting the skip re-entry maneuver, which allows the capsule to bounce off the atmosphere like a stone on water to bleed off speed before the final dive. Every single one of these steps has a 0% margin for error. If the Sabatier reactor clogs, if the supersonic retropropulsion fails, or if the MAV doesn't ignite, the crew is lost. We are no longer just looking at the stars. We are building a multi-billion-dollar interplanetary supply chain to ensure that the first humans on Mars aren't just visitors, but the first successful survivors of the most dangerous trip in history.